The accordion effect, the consequence of polarized light in precision radio velocity spectrometers. I think it's about the EPRV.
Yes.
Yeah. Okay, so the floor is yours.
Can you hear me okay? Good. Okay. Great. Yeah. So hi, everyone. I'm Rose. Yeah, this is about PARV, but thankfully I don't have to give a full instrument talk. I'm just going to be talking about something very specific. Thanks to the organizing committee for any time to talk. Super excited to be talking about polarization and how we can start thinking about it as a community. My affiliation on the slide is UCLA IR Lab. I just started a postdoc there, but the work that I'm going to be about, I mostly did for my graduate work at Columbia. So yeah, okay, so PARV, the Palomar Radial Velocity Instrument, is a PI instrument at Palomar, led by Gautam Vasisht at JPL. It was a joint effort by JPL, Caltech, and the Museum of Natural History to get this thing together. And so we've heard about a lot of different spectrographs today. This one is unique or is special because it's diffraction limited. We're using single mode fibers. It's pretty wacky. So this is just some specs of PARV. It's a J&H band spectrograph, a nominal resolution of average of 100,000. I want to point out that the delta RV per pixel is about 1 kilometer per second. So if you see pixels in my talk, 1 pixel is about 1 kilometer per second. And so we're trying to get sub millipixel precision. This is just a little schematic of the instrument. Of course, we have our fiber injection unit. We are using the Palomar's P3K adaptive optics system to inject light into our single mode fibers. There's a little single mode fiber chain that goes down into the ground floor of the observatory where the spectrograph lives. And also in that room, we have our wavelength references. So we do have an EOM LFC. We also have a Fabry-Pro Etalon and some gas cells. So I'm going to be talking about data from using both LFC and the Etalon. Yeah, so here's the optical path, and I want to talk about it because this polarization stuff, this is where it happens. So we have our pseudo slit where we inject. We have an option. We have 4 different channels, so we can have 4 different traces on the spectrograph. It goes through an OAP collimator. We have an R4 shell grating, through a transmissive cross-dispersing prism, a 3-mirror anti-stigmatic camera, and then we are imaging this with an H2RG with a broadband filter. The cutoff is, I think, 1.7 microns, 1.75. I also included an image here at the bottom left of what it looks like when it's illuminated. We have a science channel and a reference channel. This is our optimal observing mode. We're doing simultaneous wavelength reference with the LFC. Okay, so that's PARV. Now let me tell you about something that I found when we started commissioning that I've called the accordion effect. And so the way that I want to go through this is I want to describe what it is that we're seeing and how it affects our data. And then I'll walk you through how we diagnosed it and how we're going to mitigate it. But it's really important to understand what it's doing to the data. So the top slice that I have here is a difference image of the LFC illuminating our spectrograph. And you'll notice that there are these areas where a portion of the PSF is brighter and a portion of it is darker, and it seems to change across the trace. So this is a very, this effect is, the PSF is moving across in a shell order. And I've also shown that with an extracted 1D spectra of the LFC. There are two spectra in the middle panel, black and red. And I've also shown where the center of those lines are. And then the bottom panel is very important. That's the difference between the LFC, where the LFC was in one image versus another image. And the units here are in pixels. And so we're seeing that LFC spots can move half a pixel from one exposure to another right after each other, which again is about 500 meters per second, which is big. Because I should have mentioned that. We're aiming for a meter per second precision with this instrument. Okay, so that's what it looks like. What does it mean? How does it affect our data? So now what we're looking at is etalon light going straight into the spectrograph, or this straight into the spectrograph, and then we've also put etalon light up. We've put it into the single mode fiber, so it's going up to the telescope, and then it's going back down into the spectrograph to simulate science observation. And what I'm showing you is the average motion of the etalon spots across the single order in the reference and the science channels. And so since we're aiming to use simultaneous wavelength reference, these lines should match each other. That's the goal. But what we're seeing is that when the telescopes lose, we are seeing these really big shifts. These are tens of meters per second of shifts when the telescope is moving. So it can be seen pretty clearly in the static wavelength solution, which, as we've heard, is not quite as important for EPRV because EPRV cares about relative motion, but it's certainly interesting to look at. So what I have here on the bottom left are a couple of wavelength solution residual plots. And so this is showing, the units are a little difficult, sorry, but the panels on the left are all on the same Y scale, and it goes from about 1,000 plus or minus 1,000 meters per second. So in the most extreme cases, we're seeing amplitudes of 1 kilometer per second that's induced by this effect. And then on the right are PSDs showing the highest power frequencies that we see. And interestingly enough, we see the same 3 frequencies in these different tests. So these tests, we realized that we have this polarization sensitive instrument. And the middle panel is actually with the polarization scrambler, and that's why it's so clean, is because we've taken the polarization out of the light. So what's going on? Oh yeah, and then it also, of course, affects the stability. This is an Allen deviation plot of how the two channels are following each other, and the kind of stability that we can achieve within a night. So with we have 2 different prisms that we had a spare uncoated prism laying around. That's what these 2 different tests are. And when the polarization scrambler is on, we can get about 1 meter per second within a night, but it's not ideal to use the scrambler. I'll explain why in a minute. Okay, so that's what the data looks like. And it took us a little bit to figure out what was making the data look like this. And we eventually landed on polarization sensitive optics. And so we created a test bed where we tested the polarization sensitivity. We took the key pieces of the optics, we looked at them warm, and we put a linear polarizer before and after the cross dispersing prism, and found that that was the optic that was causing this effect. So on the right, I'm showing that difference image, or a similar difference image of the LFC. And you can see how the spots are changing or moving relative to each other. And then the bottom plot is still not great because the intensity, you're seeing that there's an intensity difference with the LFC from image to image, which is not ideal, but they're in the same spot, which is good. So with the linear polarizer, in combination with the linear polarizer, we figured out that it was the silicon prism that we were using. So we ran some Zmax to analyze just how sensitive the prism was, or to determine how the prism was doing this. And so the birefringence of silicon is 10 to the minus 7. It's delta n of 10 to the minus 7. And so what that means is the two different polarization states of light are seeing two different indices of refraction, and the difference between that two indices of refraction is 10 to the minus 7. We determined that we were seeing an effect that was closer to a delta n of 10 to the minus 5. And so we put that into Zmax simulations and confirmed that when you change the crystal orientation axis of your silicon, it impacts where the centroid, the PSF centroid, is on your detector. It's also wavelength dependent. We confirmed that it's wavelength dependent, and not only is it wavelength dependent, the centroids will shift within an order relative to each other. It's just a big mess. So the other key component here is the single mode fibers. We've heard about a lot of multi-mode fiber instruments, these seeing limited instruments that have to worry about modal noise. Single mode fibers, you don't have to worry about spatial modal noise, but you do have to worry about polarization modal noise, because you have these two polarization states that are basically getting delayed as they go through the fiber in different ways. Okay, let me try to wrap this up. So we found that we were inducing some birefringence on our prism based on the mount. So the mount was squeezing the prism, and that was increasing the birefringence of the silicon prism. And so we adjusted that, and we do see the instrument is performing much better. So the bottom right plot is again showing etalon light that's being fed straight into the spectrograph, and then also up to the telescope and back down with telescope slews, and they track each other much better. So that's good. But there still is some residual accordion left that you can read about in my paper that should be coming out soon. Okay, so conclusions. PRV has updated their prism mount system, which has significantly reduced the polarization sensitivity of the instrument. And it's also been motivation for high specs fully reflective optical prescription, which you'll be hearing about right in a few minutes. And then I really want to talk about polarization with people and how this is going to affect instruments. So please come up to me during the week, message me on Slack, whatever. I think that there's a lot of really interesting stuff that we're going to have to talk about. Because we can all learn from each other, and as my meme indicates, we have to keep iterating and passing our information on. So yeah, thank you.
Thank you, Rose. That's exactly the spirit, as Surat said, of this meeting, is to share not only things that work well, but also when there are difficulties. So are there questions?
I have one. You mentioned a polarization scrambler. How does that work? Is it?
It's an inline polarization scrambler, and I think it squeezes the fiber. And so during a single exposure, you manage to populate all of the polarization states. I'm not exactly sure how. I think it just squeezes it.
So thanks a lot. You said it was very important for single mode fibers, but then, okay, in the near infrared, even if we have multi-mode fibers, we don't have a lot of modes compared to the visible. So how does it go if you start to add modes? Do you have an idea?
I'm curious I'm not sure. I think it's a good question to start thinking about. I don't know how this is going to affect the multi-mode fiber instruments. I don't know if the polarization gets scrambled when you guys scramble the modes. I'm not sure, but it's a good question.
One last question. I think Gasper. So where is the microphone? Sorry, I think the one.
So this effect that you mentioned, you saw them only from the laser frequency comb, because I expect the light from the comb may be highly polarized.
Yes.
Depends exactly from the comb you have.
Yes. So I should have mentioned this. Yes, the LFC is highly polarized. And so it's exacerbated with the LFC, but that's why I mentioned this was Etalon light. So this should not be as polarized, but what the single mode fibers do is they will induce some polarization state onto light. That's something fun that they do.
Okay, thank you very much, Rose, again.